equilibrium, and what we have learned so far for two systems, first and second system, could be two phases, or it could be two phases like liquid vapor, liquid solid, whatever. And the equilibrium or stability says that thermodynamic stability says T1 equals to T2, T1 equals to T2, and mu1 equals to mu. And this is the part what we wanted to address yesterday. And this is the chemical potential. Chemical potential for two phases. They are equal, and how to measure chemical potential, because chemical potential cannot be measured so easily, because we have seen mu minus mu Ig Tp, which is T tending to 0 to P, which is having V minus P by V prime dP prime. Okay. Because if you look at the integral in the dP plane, because when the thermodynamic equilibrium exists, in any case, chemical potential one can estimate based on equation of state. It's not a big deal. The TV plane, we have done the similar procedure in the departure. The point is, when you are talking about thermodynamic equilibrium or stability, when you look at the conditions, the temperature of both phases will be equal and pressure will be equal. And if you look at our diagram, okay, this is like a particular temperature. Along this temperature is constant, you know that, right? And this is the place where we have vapor liquid equilibrium, right? The process is existing, and when the pressure is constant, P sat. So you can see that along this temperature is constant, along this temperature constant, also the pressure is constant. But the only thing is that this is your V liquid and this is your Vg. And you can clearly see VL is not equal to Pg. Okay? So and this VL and Vg can be obtained from the equation of state. So a lot of things actually there to at the stability when the two systems actually they are at equilibrium. Then the point is, it is better to talk in terms of temperature and pressure, because they are defined and they are equal for both the phases of both the systems. So in that case, this integration it seems not defined, not determined properly. You can say indeterminate. And in that case, we cannot. It looks like it is difficult to calculate the chemical potential. It is difficult to calculate chemical potential based on temperature and pressure data. So we came up with alternative definition, alternative replacement for the chemical potential, which is the fugacity. And what we actually talked about, we talked about this quantity, and we said that if we can actually have ln f or we started to do f by p as exponential of mu minus mu Ig Tp by RT. Right? And what's that thing? If you look at a very interesting thing, in this quantity at p equal to 0 will be 1, will be 0. Okay? So it's e to the power 0 equals to 1. So it looks, it is this definition, and y divided by RT, there is a unit consistency. You need to have the unit consistency for because if you look at mu minus mu Ig, this kind of some kind of suitable definitions, what you can talk about. There's a convention, you can have something else also. Doesn't matter. This is the way we can actually suitably define. And this is so this fugacity as a unit of pressure, what we actually discussed yesterday, as a unit of pressure. And we have ln f by p, which is mu minus mu Ig Tp by RT. Okay? So you can have, and this f by p is further defined as fugacity coefficient. So this much we have learned. So what we have learned, RT ln phi, which is nothing but your departure of chemical potential. And then we also derived from this, starting from mu1 equals to mu2, we derived f1 equals to f2, and we derived phi1 equals to phi2. Right? This is f1 equals to f2 and phi1 equals to phi2, both both actually are getting, because of pure phase, we have pure substance, we have multi-component substance, we will have different kind of stuff that will be discussed, is that will be discussed later on. So that's the situation we actually came up, and then what we'll be talking about for this, when we talk about the P1 equals to P2, that is nothing but P sat for the equilibrium. So the equilibrium is P sat, saturation pressure. Now the right time has come how to determine the saturation pressure. So this is the place where you have vapor equilibrium, and the pressure is saturation pressure, P sat. Pressure is saturation pressure, P sat. The point is this graph from physics. This graph is from physics, and one has to have mathematical formalism to see the behavior. And mathematical things is the cubic equation of state, what we have discussed long back. And if you see what we, for the cubic equation of state, this is my cubic equation of state. The question is, where is my P sat? Here, here, here. So your P sat is such that this area should be equal to this area. Why? Because you have to replace this by the physics. If it is not equal, then if you want to have integration of PdV or some other kind of integrate the path, then you are getting different result, and that is not the correct way. So you are saying that okay, this line will be the, and this middle line you don't know, that you have to find out. So this area, how to prove it? How to prove it? Okay. So to do that, we started doing in a formal way. So this is the point, first point. This is like calling I. Then this is the second point. This is a 2 prime, right? This is third point. This is 3 prime point. Sorry, this is the third point. This is, and this is your 4th point. These are I. One is I prime and one is I. That's how my diagram, distance diagram, right? This is I prime, this is I. Okay. And we know that at this point where we have the equilibrium, thermodynamic equilibrium with two phases, temperature equals to temperature of vapor equals to temperature of liquid. At equilibrium, two to three line, temperature equal to the vapor liquid or vapor phase, PL equals to PV, and FL equals to M. Zone 2, 3. So the basic equation. So mostly we'll be using this. So this we can treat as your governing equation. This you can treat as governing equation because temperature, pressure they are all known, and also the saturation pressure, how to determine and all are discussed in a short while. So let's look at our objective is in the P sat is known, the pressure is known. This P1 equals to P2 equal to P sat. How to prove that those two areas are equal? If you cannot prove it, then there is no point to replace this by this. And if you cannot replace physicists and mathematicians, they don't agree well, and there's a big problem. You don't know what to use. They have to agree. Okay, so our basic definition is RT ln F by P, which is P equals getting to 0 to P minus RT by P prime dP prime. Equation number 8. Now at point I, which is the vapor phase, right? Point I is the vapor phase. At point I is the vapor phase. Okay. So in that case, you can write RT ln. You can say that TL equals to TB equals to P. So RT ln AP by PI at the point I, pressure is PI, P tending to 0 to PI, Vg minus RT by P prime dP prime, equation number P, right? At point I prime, at point I prime, at this point, this is a liquid zone. How to get from here? So if you want to use the equation, this almost when you draw the mathematical equation, you have to go by mathematical path. This is a physics path and the mathematical. So to reach this, you have to use the mathematical equation. So to reach from here, you have to go, you have to come here, then come here, then come here, then come here. That's the way. And why you have to use the path? Because you have, when you define this tuberosity, equation number A, your reference is P tending to 0. The reference is P tending to 0. Then you can ask, so then I can write directly, one can ask, sir, I can directly write P tending to 0 to P VL minus RT by P prime dP prime. And I say wrong. Why? I say wrong. Why? Like that I can also write and finish the job. I am not writing it. What? Pardon? Any answer? Who is giving the answer? Who is that? Okay. Volume of liquid is not.
Till PI it is gas only.
Not the answer. Not the right answer. Volume of gas is not equal to volume of liquid. Fine, but you can say that at this path, volume of gas is also changing. Okay, that's okay. At this, when you talk about this, volume of gas is changing in the entire path, right? Point to point. Correct? Yeah. Volume is changing. It's a continuous function. It's a continuous function. It's not a discontinuous function. What's the problem? If I use it, what's the problem? What's the problem? What is your VL? This is your VL, right? If you use it, what are you doing? I was expecting the answer, but you are not giving me the answer. This is your graph. You are here. Your P tending to 0 means your data is here. You are following this path. Right? If you use the same formula, that means you are saying, you can extend this, you can say you are here, you are going by this path. That means this path is not non-existent. This path is not there based on equation of state. At this point, I know only this one. Okay? If you take this and take this path, so this much error you are making. That's a big error. So you have to start from here, go all the way to follow the path. Because this path is not available. Just like a road block. This road is blocked. Only this road is available. This answer I was expecting from you. Okay? But unfortunately, I could not get anywhere. So this is not correct. Please write down what I said because it is not available in the book of the molecules. Okay. So you have to follow the path. So P tending to 0 to Pi. I am starting from, this is my 0 point. This is my 0 point. Okay. I am starting from, so if you want to have the proper diagram, because it's going, 0 should be here and I with the 4 points. So I am going from P0 to Pi, which is Vg minus RT by P prime dP. Next will be, as I said, this is P max, this is P mean. Next step, we are following the path. Next step,
Pi to P max.
integral Pi to P max, then integrand, what it will be? Integral. Any hand please? Panda. Vg minus RT by P prime dP prime. Next step. Next step. This is unstable salt. The gas, this is liquid. Okay. This is unstable path. So we are actually having gas path, unstable path, liquid path to reach the liquid point. Okay. Next step. You know the path. You know the path. I want the answer. Integral P max to P min. Yeah, that's what you should know. If you don't know the answer fully, yeah. What B?
VG.
VG, why?
Which VL?
That's what I'm saying. If you don't, you are not. VU minus RT by P prime dP prime. Unstable path. Next step. Next step. Next step.
P minimum to PI dash.
Only you are talking, nobody else. Nobody else. Yeah, Panda. That's what I'm saying. Only 2-3 guys are responding to me. Out of 40 people. Yes. P min to PI dash. P min to PI dash. Okay, then VL minus RT by P prime dP. That's all. So simple. So I'm starting from here, come here, then come here, then come here, then go here. Over. That path I have to follow. There is no other way out. Okay. So this is my equation number C. Now, what actually happens at equilibrium? If I prime and I are 0.2 and 0.3 respectively, at equilibrium, that means what I am saying, this is your I prime and this is your I. If I prime and I, they are 2 and 3, right? What actually happens? Pi equals to Pi prime, right? This Pi equals to Pi prime. So, in that case, you can write FB equals to FL, equilibrium. Compare equation B and C. If you compare equation B and C, you get some interesting stuff. These two are equal. Pi is Pi prime, sorry. Pi equals to Pi prime. FB equals to FL. T is same, R. So this will get cancelled. What will you get then? This equals to this. So you get some nice and interesting stuff. What do you get? Just look at the board and tell me. Answer is there in the board. I am not asking anything extra. You get 3 terms. 3 integrals, right? You will get 3 integrals. So this and this will get cancelled if you compare, and sum of these 3 are equal to 0. Okay? So you will get Pi to P max Vg minus RT by P prime dP prime plus P max to P min Vu minus RT by P prime dP prime plus P min to Pi, which is VL minus RT by P prime dp prime equals to 0. Then when I am saying pi equals to pi prime, so doesn't matter. We can write pi or pi prime because at equilibrium both are same. Pi and pi prime doesn't matter. You can write pi prime, you can write pi, both are same. From this, is it possible to prove that two areas are same? From this, it is possible to prove that two areas are same. How to prove it? I only have these three. Sum of these three equals to 0. I have to prove this is my area A1, this is my area A2. I have to prove that A1 equals to A2. I have to prove A1 equals to A2. How to prove it? So this you can reduce further to help you. I'll reduce further. This area wants, if you want to look at the area, you can look at this street. This area means, so this entire area is what? Integral V dp, right? Integral V, not V dp, V dp. Okay. This graph is Vg. Okay. So this area means what? This limit is Pi to P max. This area is what? Vg dp prime. What do we A1 then? Is not A1. I am having this area. This area means this entire thing. How to get this area? Subtract this area. What is this area? Just I don't want any buzzing. If you are confident, please raise the hand. Tell me the answer. Yes, madam. P max to pi. Pi to P max is my limit. No, I'm just saying that, how to get this area. Forget about this. How to get this area. I did pi to P max. Generally, integration, what we do? We go from lower limit to upper limit. This is pi, this is P max. When you have area, and I am now teaching integration. Integral y dx, we talk x1, x2. I will talk x2 to x1, right? As far as x1 to x2, lower limit, upper limit.
Integral vi to.
Yeah, who is that? Yes.
Integral
No, I want the answer. You have the. Are you confident about the answer? This is the area for this entire string. I want the area of this region. This region.
Integral p dv from v to vg.
This region. What's the answer? Area.
Minus integral p dv.
P dv. Where is P coming? My area is here. I am talking about this strip. That means what? Integral P dp. P dv is not coming. Two hands are there. That's all. Nobody else. Sir, can you try? Next. Manikandan, right? Yeah. Can you try? No. How to get this area? Sir, I am asking very simple question. I'll tell you what I am going to kindergarten level. I want to know this area. What I will do? I will take the full area minus this area. I will get this area. Sir, this is 10. Let 10 plus 2. I am actually begging the answer for 10 plus 2. Not even BTech first year mathematics. I am begging for 10 plus 2. And it's being recorded and it's dangerous actually. So I'm teaching MTech course, asking for +2 level, from +2 level. To get this area, you have to, this is the area minus this rectangle. I will get this area. I am asking same kind of thing. Yes, sir.
Integral pi to p max.
Pi to p max.
Du dp.
That's the answer. Huh? That means you will be getting this area. You are not getting the full answer. Shall I teach that one in the class? I'll just get some partial answer.
Integral
pi to p, not p1. No p1 is there. Vu dp. Last two answer I could not get, except two hands and their partial answer. I'm really frustrated, or I shouldn't show my frustration because then you may feel bad. I shouldn't say frustration because that's the thing I should expect from you. Even +2 mathematics I will discuss in the class. Is it clear to all of you? If it is clear, then what will be A2? This area. What will be A2? What will be A2? What will be A2? A2 means, again, this area I have to take minus this area. So, I just one hand please. I don't want any kind of prompting. Yes.
So p mean to pi.
P mean to pi.
Vu dp.
Vu
dp.
dp prime minus P mean to pi. VL. I'm asking something very simple. Okay. Now you have to prove. How to prove from here? You understand the problem. What you have to prove? Okay. From here, one thing you can see from this equation number D, you can say, you can directly write pi to p max Vg dp prime plus p max to p min Vu dp prime plus p min to pi Vl dp prime, then RT prime dp prime. So RT ln p max by p min pi. It will be RT ln p min by p max. It will be RT ln pi by p min, and all will get cancelled. So this will be equals to 0. All will get cancelled. Ln a by b is ln a minus ln b. If you apply that, you can see all will be getting cancelled. So you are left with this expression. Question is, from here, can you prove this rule? So we have Vg dp prime, and we need to have this pi minus p max. So it is, we can actually write this as this. You can actually add and subtract. So this Vl dp prime is there. You can actually see that p means, if we go there, it is sign will be changed, and you can see that magnitude wise. So it is why it will be coming a1 equals to minus a2, and of course, when you talk about one, if you are going from one direction, so other direction will be negative and positive. The area has some direction. Okay, so it will be seeing a1 equals to minus a2. From this method, the magnitude wise, both there is are equal to same. So from here, we can actually see this can be proved, and area is actually the area of a1 equals to a2. Okay? Because why I am getting negative? Because when I consider this pi to p max, but this data will be changed. Here is p min to p min. So this because of this data, I am getting a1 equals to minus a2. But the magnitude of the area cannot be negative. But the mathematically you are saying the data is otherwise it is same. Fonda clear? Yes. Okay. So Maxwell equal area rule has been proved. Everything is clear from Maxwell equal area rule. So that means it suggests that since you are having that, then you can peacefully delete this, peacefully delete this one, because they are saying, so that means instead of going by one entire path, I can just go like this. So what we have learned, so your part is, this is your equilibrium line I, this is A, B, C and D. Final point and final destination point, and this is PV, this is Pmax, and this is your saturation pressure of P. So what we have seen that if you go like this and if you come like this, so both the part A, B, C, D, part A, B, C, D and part A, D are equivalent. Part A, B, C, D and part A, D are equivalent. So that means the common question actually I asked, I am compressing it, I have a cylinder. We have seen this kind of problem long back when you have physical chemistry book. You have gas. While compressing, gas has become liquid. While compressing after one point gas has become liquid. Yeah, gas has become liquid. Gas has become liquid. What will the work now? The phase change doesn't work. Phase change doesn't there. So integral W equals to integral P dV, point 1 to point 2. You apply the equation of state. It's ideal gas. It's RT by P, and then or if you can write in terms of V, you can get the answer. But the phase change is occurring. Of course, ideal gas will not be valid because in this region ideal gas cannot be valid. You can have Van der Waals equation of state or the Payne-Robinson or SRK. My question is how to get work done from the front. You are having a piston, gas is changing to liquid. How much is my work done? Very simple question. How much is my work done? How much is my, so this is the vapor part. Okay, so I am here. First point, second point is here. I am here. I am going there. Okay, my pressure is increased, of course. I am doing that. Pressure is increased. One pressure at 1 less than pressure of 2. At point 2 it is liquid. At point 1 it is vapor. What is my work done? How to calculate the work done? Because gas is being changed to liquid. And work done formulas I know. W equals to integral P dV. What is my work done? What is my work done? Yes. And at this, and one thing I should tell you that entire process is isothermal process. Because if it is not isothermal, then you cannot use this part because it is isothermal process. At this point temperature is constant. So this is WT, isothermal process. Isothermal process. If it is not, it is a problem. If it is adiabatic, we have to have different formulas. Isothermal. Isothermally I am doing it. What is my formula for work done? 1 to 2. 1 to 2. What is my work done? Asking a very simple question. You have a piston assembly, pressing it, vapor is gone to liquid. What is the formula of the work done? What is the formula of work done? What is the formula of work done? No idea. Simple question I am asking. Simple question. Can you tell me the path of this in this diagram?
Linear path is followed.
No, what is the path? This is my P, this is V. I am here at this point 1. How I will go at this point 2?
A to D.
Okay, who can? Yes.
1 to A.
Okay, next.
First we have to follow the curvilinear path.
This price come. Okay.
Then we have to calculate the P-sat.
This is my A point.
Then we should read the linear path.
B.
Plus isotope.
So it will be 1 to A. It is 1 to A. P sat dV plus B to 2 P sat dV. The point is, it looks like same, is not. This is vapor domain, this is liquid domain. Why they are different? Because A and B, van der Waals constant, will be different for liquid and vapor. Okay, so that's the way one can actually calculate. So this is and also this one, sorry, A to B, that is called heat of vaporization, delta H. That part. I cannot remove that, so that part has to be there. That order. This is the phase change. That phase change work has to be taken care. So 1, 2, 3. 1, 2, 3. 1 to A P sat dV, B to 2. This will be supplied. How much sheet of vaporization, how much negative for the solid liquid. So this will be supplied. So P sat dV, B to 2, and delta H. Okay? Because if you would have followed the same, you have to take all those things. So I am just cutting it. Now everything is fine? Panda clear here, right? Okay, so that's the 3 part will be there. Okay, and only thing is that you have to supply, and then you can actually calculate. And 1 to A, if you want to have the V domain, so in that case you need to have V1 to VG here, and here it will be VL to V. Okay. Now you can see how much effort. If it is in a gas domain, ideal gas, written in the books, they say like this part is actually your ideal gas. That means when you talk about your PV diagram, these are critical point, and the books actually talk about this part. Integral PdV, they put RT by V, that's it. RT and V2 by V1, your job is done. So simple. But you are working in this domain, and that's why so much problem. Always books give the simple thing. They won't talk about complicated stuff. Okay, so now we'll be talking about still the point is unresolved. How to calculate saturation pressure? I said that if I know saturation pressure, it is possible to prove Maxwell equal area rule. That is called as, this rule is called as Maxwell equal area rule. That is called as Maxwell equal area rule. Okay. We know assuming that P sat is known. The P sat is not known. Okay, we have to calculate P sat. For that purpose, you need to calculate fugacity. To calculate P sat, you know that at P sat, phi L equals to phi V or FL equals to FV. So to calculate P sat, basic equation is phi L equals to phi V or FL equals to FV. Okay. The question is, you need to have the knowledge of fugacity in the liquid phase and the vapor phase. How to estimate fugacity? The next question. How to estimate? Because we said we could not estimate chemical potential. So that we are doing fugacity. If you cannot estimate fugacity, then the whole purpose is gone. Right? Because you can estimate temperature, you can estimate pressure, you have to estimate fugacity. Right? So how to estimate? Let's say fugacity coefficient. How to estimate fugacity coefficient? So you have ln phi, which is 1 by RT mu minus mu ij, or you can say 1 by RT G minus Gij, whatever. Gives energy and chemical potential both are same. This is nothing but 1 by RT P tending to 0 to P d minus RT by P prime dP. This integral you solve in the V domain, in the departure calculation, right? V dP prime, what did you do? V dou P dou V dV. RT P prime dP prime, you put RT P prime dou P prime dou V dV. You have done it. Okay? And if you do that, what will be your formula of ln phi? You have the notes. Please look at the notes and tell me the answer. Everything is there in the notes. Both the integral have separate formula. We have done it in departure of entropy calculation. Entropy departure, S minus Sij. Look at this. Both the integrals have been evaluated and give me the answer. Ln phi. Just a minute. Ln phi equals to 1 by RT, then start. What is that? Z minus 1. Z minus 1. Plus or minus? Plus or minus? Ln Z. Plus you can put V equal to infinity to V RT by V prime minus P prime dV prime. Agreed with me? Yes or no? Yes. This is the fugacity formula for the first principle. You can verify this if you know the departure formula of enthalpy. If you know the departure formula of the entropy, you know that G minus Gij equals to H minus Hij minus T into S minus Sij. Departure formula. So you know G equals to H minus Ts. So G minus Gij Tp, which is H minus Hij Tp minus T S minus Sij. So you know this and this. If you combine it, you should get the same result. Okay? So both the ways. So these are this from the first principle. And this is for the cross-checking, verification. I always go by the first principle. That's always better. Okay? So if you do that, so let me talk about how to estimate the fugacity coefficient for liquid and vapor. You have to estimate liquid and vapor, right? Phi L and phi B. Okay? So fugacity coefficient has been estimated to the first principle. Fugacity coefficient. So that's one good news we have. We have now estimated fugacity coefficient, and every term is possible. This term is possible to estimate. This is estimate. This is the V plane. No problem. The integral is determined. So that's no problem at all. So fugacity of the pure fugacity of pure gaseous species ln FBTB by P or ln phi B equals to 1 by RT V tending to infinity equals to V ZV RT by P RT by V prime minus P prime dV prime minus ln ZV plus ZV minus 1. I think the whole bracket should not be there. Check it out. This formula is correct. This whole bracket I have done wrong. It should be Z minus 1 minus LZ. Am I correct? Correct, right? Because RT and RT will get cancelled. Okay. Check it out. This is something wrong I wrote last time. So this is 1 by RT should be only with that. So that you can now see, to calculate phi B, we can actually use this formula. V infinity, this will be, you know the ZV, compressive factor, RT by P, you can evaluate this from the equation of state, and these are all known. And how we are knowing this? From the Carnot's method. The Carnot's method you get the Z, you get in terms of Z, right? Carnot's method gives the solution in terms of Z. Carnot's method gives the solution in terms of Z. So at low pressure, ln FBTP by P, which is 1 by RT, P tending to 0, P, V minus RT by P prime, dP prime. Okay? So this comes at low pressure, what will happen? At the low pressure, Z equals to 1, right? Okay? So ZB minus 1 equal to 0. ln of 1 equals to 0. So you get. So at the low pressure, if you are doing low pressure calculation, this is the way you can estimate phi B. This is the way you can estimate phi B. And this FBTP at low pressure, at P tending to 0, FBTP even can be written as P. That's the basic definition of fugacity coefficient. At P tending to 0, this integral will be going to 0. E to the power 0 equals to 1. So FP is equal to pressure. Okay? So you can also have expression of in terms of the compressibility factor of the fugacity for the V. Liquid you cannot do much approximation. So another expression ln FB TP by P, which is 1 by RT, P tending to 0 to P, V minus RT by P prime dP prime, which is 1 by RT, P tending to 0 to P, Z RT by P minus RT by, P prime dP prime. This V equals RT by P in terms of compressive vector chart, and which is nothing but P tending to 0 to P, Z minus 1 dP prime by P. RT will be cancelled. So then you have the Z versus P curve and all those things, Z versus P curve. So in the compressive vector chart, you can also calculate the fugacity coefficient. So I will end up now here, and next class I will proceed further.